Hello everyone, my name is Dongwei Jiang. This is my presentation for our AAAI 2025 paper, Self-Incorrect, LLM Struggle with Discriminating Self-Generated Responses. This is a joint work done with friends and colleagues at Johns Hopkins University. This paper is about the self-improvement capability of large language models. But first, let's talk about why does this matter. Some people worry that the possibility of AI self-improvement could lead to AI surpassing human intelligence, and it might bring potential existential risks. However, to some other people, this potential can also be viewed as an exciting goal for making AI models stronger while maintaining their safety and assuring new breakthroughs in technology. There has been a lot of research works in this area, and there is actually a debate in the research field over whether intrinsic self-improvement, the kind of self-improvement that only relies on our own judgment but not some external feedback, is achievable. Those four intrinsic self-improvement claims that LLMs can self-improve, while those against argue that LLMs cannot self-improve yet. This naturally seems like a contradiction between findings, which motivates us to revisit this goal from a different perspective. In this work, we propose to break intrinsic self-improvement into two disjoint but related capabilities: generation and discrimination. The motivation comes from human life. A crucial aspect of human growth involves reflecting on one's own actions and discriminating between actions, ideas, and alternatives in life. The choice that one makes should surpass the alternative choices in order for one to continue to progress further. Or in other words, a human that continues to make effective decisions and grow typically has strong ability to discriminate among their options. This should also apply to LLMs, but is that even true? It's actually not straightforward to conduct a fair comparison between generation and discrimination for LLMs. That's because those two capabilities are often measured with different metrics. Generation is typically measured via RAG, those generation matrix, and discrimination is often measured via classification matrix like accuracy and F1. Parallel compares those two capabilities directly, even though their metrics are not directly comparable. To address this challenge, we provide an evaluation framework that allows apple-to-apples comparison of generation versus discrimination. Let's first look at the generation setup. During generation, we sample multiple answers from the model with a non-zero temperature. Then we randomly select one of the answers and apply the evaluation metric F to it, and use the result as the metric for generation for this test sample. In this case, the evaluation metric is exact match. The overall generation performance SGen is the average across all samples in the dataset. During discrimination, we work on the same set of samples. We create a discrimination prompt that takes in all those samples and asks the model to determine which sample is the best and output the index of that sample. In this case, it's 4. We then apply the same task metric to the chosen sample. In this case, it's A4. And the overall discrimination performance is also the average across all samples in the dataset. Notice that the comparison between generation and discrimination is fair, because we are operating on the same set of samples. They have the same upper and lower bounds. With this setup, we can present our self-incorrect hypothesis. LLMs are not reliably better at discriminating among previously generated alternatives, which is measured by SDICT, than generating initial responses, which is measured by SGen, and hence DGDiff, which is defined by SDICT minus SGen, is less than or equal to 0. We treat self-incorrect as the null hypothesis, or H0, to provide an objective basis for testing. To reject it, or to prove that we are wrong, it must be demonstrated that dgdiff is a sufficiently large positive value. We tested our hypothesis across several mainstream LLMs and tasks, and the conclusion is that on a dominant majority of experiments, first, dgdiff is small or negative, which is shown in the figures by comparing those blue bars and red bars. Second, the p-value, which is what we use to reject self-incorrect, is greater than 0.05 in 54 out of 56 cases, which means our hypothesis self-incorrect is not rejected. And what about scale? The scale has an impact on self-incorrect. We find that even for larger models, dgdiff is still small negative, but stronger models tend to be better at discrimination, meaning that they have a larger dgdiff. Having established that, the next natural question to ask is why is discrimination not easier than generation? We have a sub-hypothesis that states autoregressive projective is related to our hypothesis because the pre-training process of autoregressive models is more similar to generation. We have tried to replicate the experiments on flan-EUR2 and flan-T5, two models that are not purely autoregressively pre-trained. And the results seem to support this hypothesis because the dgdiff of flan-EUR2 and flan-T5 is sufficiently large. Now let's go back to the contradiction. We now see that some of the papers that claim LLMs can self-improve relies on external feedback. However, self-refined setup doesn't seem to depend on external feedback. To further resolve the contradiction, we replicated the experiments in self-refine. Those are the experiments we replicated. And during replication, we find that there's actually some issue in evaluation setup. Certain aspects of tasks can be exploited for increasing task matrix without actually understanding the task. Let's take constraint generation, for example. The task involves generating a paragraph that includes all the predetermined keywords, and there is a feedback mechanism to help the model self-refine. And this is an example trajectory we observed many times. During iteration 1, the model just generates a passage which contains some of the keywords. And the model also generates some feedbacks by itself. And if we look at the feedbacks closely, we find the feedbacks actually only contains low-level hints about the expected modification, which is not ideal. During iteration 2, the model just keeps extending the paragraph by appending new sentences to it. And this is the feedback for round 2, which asks the model to insert a Word doc somewhere at the beginning of the story. But the model didn't listen to that. It just keeps generating sentences and expanding the paragraph, which brings the second issue. Instead of rewriting the paragraph, the model just keeps extending it by appending new sentences to previously generated paragraphs. And as the paragraph gets longer, the matrix, which is quantified by the number of constrained terms, can only increase. It can never decrease. So in other words, even in the absence of any feedback, the generated text has some chance of containing the required terms, which naturally drives the matrix higher. So it remains unclear whether those matrix improvements stem from a genuine understanding and integration of the feedback, or it's just some chance. In addition, if the model is indeed self-refining, then the model itself must strongly prefer refined generations. But we only observe a marginal preference over refined generations. This actually aligns with the conclusion in this work. So overall, we don't think there is a contradiction between our work and the previous work. To summarize, the motivation of this work is there's a debate in the field over intrinsic self-improvement. We revisit this issue from a different perspective by directly compare generation versus discrimination. What we did was we developed a general framework for apples-to-apples comparison of LLM's ability to generate and discriminate. We then applied this framework on various models and tasks. What we found was LLMs are not reliably better at discriminating among previously generated alternatives compared to their ability to generate initial responses. Note that our claims in this work are limited only to intrinsic self-improvement. Extrinsic self-improvement remains a valid methodology. There are also some limitations for this work. First, this work can benefit from expansion over more models and tasks. And it's also hard to determine models' true answer preferences. Also, fine-tuning could improve models' discrimination capability, but it may also decrease the versatility or the general performance of generation. Whether it's possible to fine-tune a model that's both good at generation and discrimination is an open question. That's it for my presentation. Thank you for listening.